And with that, we move on to geometric dimensioning and tolerancing. Now we're getting to what we really consider to be geometric dimensioning, and we'll be introducing things a lot that you'll recognize as symbols more than values. Okay? And there's a couple key thoughts associated with it. It's a system of dimension drawings with emphasis on the actual function and relationship of part features. And it's dealing with interchangeability is critical. Okay? It doesn't replace the coordinate dimensioning, and it's used in conjunction with coordinate dimensioning, but it is separate. Okay? Very, very separate from what we've talked about thus far. These will use surfaces and angles and precisions and just different aspects. As we talk about some of the aspects of it, let's focus upon this section. Because geometric tolerances are based on information related to form and positional tolerances. They use symbols to explain the information relating to characteristics such as the form of an object, the profile, outline, object, orientation of features, blah, 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 blah. And they use these symbols that we will become accustomed to seeing. Here we go. Symbols like flatness and cylindricity. It's hard to say. That's why they probably use the symbol versus the term. Parallelism, concentricity, circular runout, total runout, they're all based in symbols. And you can see the categories. This category is a form, this is a profile, orientation, location, and runout. And each deals with each one. We'll have a lot of information in the rest of the chapter about this. And the next page shows the modifying symbols, because a symbol will be used to modify a standard geometric tolerance. For example, we've got our maximum material condition, which we've talked about those. That's just an M in a circle. Least material is an L. None. Diameter. Arc length, etc., etc., etc. So, some of these you already recognize. Countersink, counterbores, square. Most of these you can probably figure out on your own. Some terms like spherical diameter, maybe a little bit new to you. So we take a look at the overall page, and it starts working through. Of course, it talks about the fact that templates are used for this, but we don't use those with CAD systems anymore. Built in. But we have a datum feature symbol, and if you were to think back to what that was when we saw that letter in a box, and saw a line, and a little darkened triangle. That is a datum feature symbol. And as shown down on the bottom of the page, something we'll be able to recognize very often. Keep in mind it has some sizing associated with the datum feature and how it applies. But basically we often use datums for reference of other objects. And as we practice it, you'll get the hang of it. We also have datum targets that are used when the whole feature is not necessary to use as a datum feature. And we can take a look at those a little bit later on. But here we have the good old-fashioned datum features and the datum references that occur. So we would definitely want to pay some close attention to what we see here on figure 1619. So basically what you have, of course, is your datum symbol there. And you'll notice that we have this neat little feature here, which is basically the format that we make geometric tolerances in. And you'll understand a little bit more as we get into some pictures and graphics and such. But essentially, you'll notice that there's one box associated with a specific symbol that relates to the previous page of symbols. For example, this particular symbol that was shown relates to a position geometric tolerance. Then you have a box that specifies some kind of modifying symbol or value. And then you have boxes that deal with referencing some type of datum. And it could be more than just one datum. See, for example, here's datum A, there's a datum D, and there's a datum E when it is most material condition, which means it would have perhaps the smallest hole or the biggest part. And you have an L here representing the condition of least material condition. Now, not all these boxes are always going to have that much stacked into them. typically they will just be about 2 or 3 boxes, or 3 or 4 boxes, and usually involve some kind of arrow, okay, as we'll see them. But this is the basic breakdown. Basic symbol starts here, some type of value or material condition symbol, and primary datum, secondary datum, tertiary datum. So it's a good example. Let's take a look at it one in practice and see if we can understand what's going on. Now at first, when you see a bunch of these things, it basically is very overwhelming. For example, let's break down this particular part. First thing you want to do when dealing with geometric tolerancing is you want to locate your datums first. So we see this datum symbol down here, and it is referencing that surface, which means this entire back surface of this part is a datum, which means it may be a dimension from, it may be referenced from, maybe doing all kinds of things from it. We may want to go ahead and reference other datums. For example, we'll notice that the C here is attached to the overall box, which means it is attached to this particular dimension. It could be this surface, it could be the surface, it could be the overall whole, probably the overall whole. Same thing is true with this datum. It means that this overall whole is a datum reference in some way. Now let's see if we can find a geometric tolerance that's based off A. Look right there. Look right there. And look right there. These 3 geometric tolerances are based off datum A. Okay? Key thing to remember. Let's start off with this one right here. Okay? First of all, we look at the symbol and we see that it is a symbol. We look back in our text and we find that that is an orientation tolerance for parallelism. Here's the value of the tolerance. This is the reference of the datum. So first of all, we look at surface A, which is the entire back surface of this part, and it says that this surface, since this thing has no arrow, it means this surface right here is parallel to this surface within a tolerance value of 0.06. What it means is we are creating an imaginary boundary that is 0.06 wide, and that this surface has to fall between it. Okay? Clear as mud yet? Well, we're going to get more into it, and you'll learn more as we go along. But that's how you basically break down any geometric tolerance. First, check out where your datums are, then check out your tolerances. Now, another term for this box is called the FCF, or Feature Control Frame. It is mentioned up right here and talks about what it is and how it works. And basically, it works the same for all geometric tolerances, just the representation. Now, there's a couple things about the feature control frame you have to understand in terms of attachment. Attaching a side or end of the frame to an extension line for a feature provided it's in a planar surface, so you can attach it to a dimension line or a feature line. You can just use a good old-fashioned running leader, arrowhead, or you can place the frame below or attach to a leader direction. Okay? So we start off with tolerances of location. Okay? We've got true position, and the best way to kind of break this down is to take a look at some examples. All right? So what we have are 3 figures that show the same piece of information. This one, of course, being the geometric tolerancing technique, and these 2 being standard techniques. Alright, so we take a look at these 3 and compare the differences. For one thing, let's talk about locational. The location is written in terms of a node. It gives a basic dimension here. It says 3. And it says locate within 0.055 in relation to true position. So there is the locational tolerance. It's just telling you, hey, it has to be within a diameter of 0.005 from its position. Which means this circle its exact position on this part has a range for its center point to be in that is in a diameter of 0.05. Not saying that the circle itself is 0.05, but saying that the center point of the circle has to be located within a 0.0055 radius. So it basically means if I have a circle of 0.005, the center point to the big circle could be here, could be here, could be here, could be here, but it just can't be out here. A better way of showing it over on this page, or on this schematic, space here, okay? Here is the target spot, all right? And then we're saying we're creating a circular zone that is technically a diameter of 0.005. And then we're coming in with our drill bit to try to drill the hole that's supposed to be 0.375, and we hit here. Okay, well that's all right. Maybe we hit here. Okay, it's in the range. If we hit here, it's great. If we hit here, it's also in the range, so it's good to go. We hit here, it's good to go. If we hit here, it's bad because it's outside of that 0.005 diameter circle. So what it's doing is create a circular zone that the center point of the big circle, the center point of this circle right here, has to be located, is the concept. Okay? Out here is bad, in here in this zone is good. So that's the tolerance. And this tolerance is given in the form of a note. Then we have another drawing that shows the same thing and creates this little breakout section view that says, okay, I'm creating a zone, a box zone, for this circle, saying that you have to hit the center point somewhere within this box, which this too also represents the same thing. It means that this circle, its center point, has to be located within this tight of a zone for it to meet requirements. However, that same information is related very simply with this particular box. First off, you have your circle information, 4 circles, diameter 0.375 plus or minus 0.002, and positional tolerance. Notice there's no datum attached to the end, doesn't need one. Positional feature, which is shown there, the diameter that's given is 0.014, which is the same equivalent of going from here, and it's shown there. So basically it's saying the exact same thing as what this does. You have to hit the center point of this circle. Your drill bit has to hit the center point within a tolerant zone of 0.014 from the specified center to center distance. So all we're doing with geometric features or feature control frames is taking this basic tolerance and turning it into a simple format that anybody can use. So one more time, it's just saying to us that here's the part. We'll say this circle is located correctly. We've got this basic 3.00 here dimension, and here's our target. Okay, then we're saying, all right, we're going to create a region, a diameter of 0.014. This is the zone that you have to get your center point when you're about to drill, and your drill hits here and makes the big circle. That's okay. If it hits here and makes the big circle, it's okay. If it hits here and makes the big circle, it's not okay. That's all it is. And oftentimes you will see diameter values used a lot in feature control frames because they create regions of tolerance. And that's the easiest way to understand it. This diameter feature shows your region of tolerance. So if you hit here, it's good. If you hit here, it's good. Hit here, it's good. Hit here, it's not good. Hit there, it's not good. Hit here, way not good. So that's all that these things are going to do in this overall procedure. I'm going to stop there with the video, move on to another one. Just let the computer cool down for a little bit, and we'll pick up where we stopped right here. We'll see you in a little bit.